Then let's talk about a small angle grain boundary. Small angle grain boundary. First, let's talk about the low angle tilt boundary, which is the situation when one grain tilt away from the other one. The two um, grains have the low index axis parallel but not aligned. Okay, and they rotate from one uh, tilt for one against the other. So for these types of low angle tilt boundary, we can view them as a array or a series, aligned series of parallel edge dislocation. And each of those dislocation has so-called a Burgers vector B value. Here it's a simple schematic. We see that on the left side we have one green, perfect alignment, and on the right side we have also another green and also with perfect alignment. But in between them, we would have a so-called low angle tilt boundary. And in fact, when you look at it closer, this so-called low angle tilt boundary are essentially an array or a series, a pile of parallel edge dislocation. You see this symbol? It's for edge dislocation, which hopefully you learned in your introduction to materials engineering courses. Or the edge dislocation, as we view from the side, is just a half plane of atom, as you see here, half plane of atoms. This one, half plane of atoms, and this one, half plane of atom. Thus, it stops here. That's why we call them half plane. And each of those edge dislocations share the same Burgers vector B. Okay, and this so-called green boundary, a low angle, as you see from left side versus right side, that's a tilting, but only for a small angle, 5 to 10 degree or 15 degree. Okay, not a large angle. And for these, we can view them as an array, a group aligned group of parallel edge dislocation. Okay, if the tilt angle from left green to the green on the right, the tilt angle, if we can measure it to be theta, which typically is small, and then if we can define the distance between neighboring dislocation, this is one dislocation, this is another dislocation, the distance between neighboring dislocation is capital D. Okay, and we would have a very simple mathematical relationship as I give here. The theta, the tilt angle theta, would be given by the ratio of B Burgers vector divided by the interdislocation distance of capital D. Okay, theta is that angle is approximately the ratio between Burgers vector divided by D. Okay. This is essentially the way that you define an arc angle. Okay, and this is the same relationship. D would be Burgers vector divided by this tilt angle theta. Okay, from this relationship, we can easily get the interdislocation distance would be B Burgers vector divided by the tilt angle theta. Okay, so this is for the so-called low angle tilt boundary, left green, right green. They tilt away by a small angle, and we have a very simple relationship between Burgers vector, the tilt angle theta, and the interdislocation distance, capital D. For the other type of low angle, we call them low angle twist boundary. Okay, it's a screw dislocation. Suppose we have one green like this, and then on top of it there's another green, but the top green is twisted for a small angle with respect to the bottom one. And when you look at geometry, it will be like a screw dislocation. Okay? Then Other than these two, there are the more general case of asymmetrical low-angle green boundary, which we show them here. Asymmetrical, as you see, low angle, the green on the left and the green on the right, we don't see a too much a difference in orientation, which means low angle, but it's not exactly like tilt boundary. If you look at the half plane, it's pointing towards different directions, as you see here. Half plane, half plane, half plane, half plane, half plane. It's pointing towards different direction. It's not exactly parallel dislocation with the same Burgers vector. Okay, these can be another type of small angle green boundary. Dislocation with different Burgers vector.